Okay. Now you can see something similar to what we had at the beginning of last week. You can see a little flashing light in front of the eye, and then, well, it's not a little flashing light, it's an array of little white and dark items that change colors, flash from black to white. You can see that this one here, which is down below and to the left of the person, lights up the cortex, and the red line again is the calcarine, and then you can see that it lights up the cortex, but in sequence here. It lights up here beside the line, the calcarine, and then farther away. So we'll see, that's what we'll talk about in this lecture, this progression of activity from here to here. So now we can take a look at what we have after V1. You can see V1 here is right here around the middle, and that's where the calcarine is. It's tucked into this valley. And then on both sides of it is V2, and on both sides of that is V3. So these are the regions that will be receiving activity. I'm going to turn the brain, and you can see how it looks like from the back side. Here's the valley, the calcarine, and you can see that on both sides of it is, well, the color isn't showing up too well here, but it should be V1, and then around that V2, and around that V3. You can see more of it down here, and again, in the very medial view, you can, the lateral view, you can see that V1 just sticks out just a little bit, and around that V2 and V3. So again, being able to see all these activities at once, things tucked into the cortex, and one's not. I've blown up the cortex of, this is the brain of one of my students, and I've inflated it. So you can see it into the student's calcarine. And you can see that there's here in front of the eye, there's one line rotating. And over these three structures, V1, V2, V3, there's these lines passing over them. And you can make sense of the one that is going around V1. You can see that as you hit this point here, you should be going down the middle of V1, and down the middle of V1 is where the calcarine is. So if you just watch that line carefully, you'll find that's true. And then when it's below the calcarine, the line will appear above. When it's below the line of sight, the line will appear above the calcarine. Okay. Now, we stop this at a certain point in time. We notice that the line here is slightly below the field where the eye is looking. Okay? It's going down below. And so if you look here, it's this line here in V1 is slightly above the calcarine. The same line is at the V2, V3 border. So it has this odd relationship. If, on the other hand, we look at a vertical line, we see that it appears this line here is as far from the edge of V1 as you can go, and so this is the very edge of V1. After that, it'll appear again up here, where the line will be in the under the calcline. So you can see here that the lines are above and below, touching V1 and V2, and at the end of V3. So what happens is that the borders form this pattern of lines, and these patterns of lines are used to demarcate where V1 begins and V2 ends in real humans. You can anatomically map it out. So this is V1, this is V2, this is V3. By basically showing them these patterns of lines that are either vertical or horizontal. Now, why is that happening? Why is this odd thing happening? It's actually not very odd. If you take a line like this, where the tail is here and the arrow is here, and look to see where it is in the cortex, well, over here, you can see the tail starts somewhere, not in the fovea, but somewhere in the periphery. And you can see that this is where the fovea is. Well, this is more in the periphery. And that's where the tail is, right on the horizontal, right on the calcline. You can then see that the head is at the border of V2, over here. And then its image is repeated, but with the arrow flipped. So this point here, a point representing this part of the visual field, is close to this point here. So similar neurons like to be near each other. So both sets of neurons are receiving input from the same part of the eye. So you want to put them together. Now, one thing that does is the following. There's a theory that it is this the neurons going from one place to another place within the cortex, and these axons here acting like springs, pulling these two together physically and producing a fold here. And they would do this. This axon would be pulling because it was connected to a similar cell, and this would make the neuron near this neuron, and this axon the shortest possible. So this fold would shorten the connections between these neurons and these neurons. Now, what are these structures trying to do? Well, they're trying to figure out what the objects are around you. So to do that, you've got to figure out where certain parts are. Like the world is filled with things like the corners on them. If I look in front of me now, I can see all your laptops, and they form little squares. And one of the first things I've got to recognize is that there's a square there in this world that I see. So how do you organize things when you have when all the retina sees is 5 lines that don't quite meet, like this, and decide this must be a square, and this is an extra line somewhere, something to do with something else, the background perhaps. And the way one theory is of how it occurs is that when imagine each of these are simple cells, and each of these simple cells sees this part of the retina and likes that particular orientation, some likes that orientation, and so forth. When these are just individual lines having no relationship to each other, these cells all will fire randomly. So at random times, it's called asynchronously. Another name for it, but basically you can see that when these neurons fire, there's no relationship to each other. One thought is that when the brain figures out that maybe that's a box, then the neurons that represent that box start firing asynchronously, and the other remaining neuron fires at a different time. So this is called binding. You bind the activity of neurons together to form shapes of different kinds. And the process continues and continues over and over again until the objects in the world are defined. It's the grouping of features. And this grouping of features then makes the activity of these neurons very powerful. So when neurons fire together, they wire together. So they go back to V1 and accentuate its firing. You know. So binding, grouping, how does it work? Well, it needs, brain is looking for cues, you know. This is the world it sees. And you can see that sometimes you would see just a random blotches. But if you look carefully, you start seeing that there's patterns. There's actually 2 giraffes in it. And see if you can figure out. That's where the 2 giraffes are. So go back again. You see that there's 1 giraffe there and 1 giraffe there. So the visual system needs some cues to assist its binding, to determine what's in the foreground and what's in the background. And when they figure out what's in the foreground, they get to group those blobs, those shapes, into forms. And one cue is color. If the blob is, of course, different color, then it's easy to group or bind them together. And the other thing is memory, past experience. So the fact that you can see these giraffes here for a minute, you can look at it and pick out the ones that were that color. So memory is very important in telling you what's happening. We'll look and see what other cues are important too. This is an interesting phenomenon. You notice that these squares, within the circle, you have this, wedge appearing that's in green. And when the wedges are in this position, you should see a square form in here. Okay, back to up in this position. Yeah. square. And sometimes you can see lines extending from one to the other part of the square where there is no line. That's called an illusionary line. It's again part of the brain trying to fill in things that it doesn't see. And again, if you look carefully at when it's lined up, you sometimes see a hue of green in this area here, because the brain is filling in the color that it saw in V1 from those double opponent cells, what color the edges were, so it fills in what the inside is with that same color. So this is a subjective or illusionary contour. And you can imagine that there's a cell here, and it fires when this edge is aligned over them. So when the two things at this point here, the cell would start firing. Yeah, now it's stationary, so you can see it easier. Okay, lines across here, and a bit of a faint green shade in the middle here, all due to filling in. So you have the visual image come to the eye. It gets analyzed by the visual cortex, and then your brain interprets what it is that you're seeing. But this interpretation is also affected by memory, which then affects the interpretation, feeds back to the visual cortex, filling things in. So, for example, when those two lines were parallel to each other, close by, the brain filled in the line in between. In the same way here, if you misread this word over here, you might not see that the letter N is here and not the letter M. If you look at this, try reading this. You find that the surprising thing is, it says basically that for a lot of reading, all you need is the first and last letter, and the brain figures out what the word is from just those two cues. So it doesn't really care what the middle is like, it'll fill in what the word is. Where does all this happen? Well, there's V1, V2, V3. You can see that the information flows through up. One arm goes up and over the top of the cortex, and goes to the parietal lobe, and it's called the Ware stream. It's involved in actions. And over here, you have another pathway. It goes under the brain, and it's the what stream, and it's involved in the perception of objects. Now, there's something like about 36 or more visual areas that we've talked about now, V1, V2, V3. Well, there's 36 and counting. I keep discovering new ones every month or so, it seems. Um, and so what the amazing thing about the brain is that it's like um, uh, your Silver City um, multi-screen theater. And you walk into there, and all the screens are playing the same movie, but each screen is different. One plays whatever motion is happening in the scene. One plays whatever colors are happening in the scene. And there's all kinds of other attributes that the different regions analyze are excel for. So one area will fire for motion, one area will fire for color. Um, and, uh, and what is amazing is that you see this object of moving in this direction and of that color, and your brain automatically uh, senses that. It sees a blue object, blue, let's say, ball going across the screen. And your perception of that blue moving ball is because it activates cells, blue cells, in one part of the brain, and it activates motion cells to the right, another part of the brain. And your ability to sense the activity of both these things and many other things at the same time determines your ability to recognize, yes, this is a ball flying in front of me. So there's no, little magic person sitting way deep inside the brain looking at this all and analyzing for you. Uh, your your awareness of the world is your awareness of all the cells that are firing at that time. It is the activity of your cells that you sense. Okay. The path that heads up, as I said, it's called the weir stream. It's also called the dorsal stream. And it goes along another important sulcus called the intraparietal sulcus. And that's involved in selecting actions to particular targets. So when I reach for a mouse, this is where all the brain activity that would happen up this pathway. And because it's involved in locations of objects that's going to reach to, this is called the weir stream. And we'll discuss more of it in the next in 2 lectures from now. Today we're going to talk about the ventral stream, and that's the path that heads under the brain. And the place that is the inferior temporal lobe. All this thing along the side here is the temporal lobe, and this is the underside of the brain that we're going to be talking about. And this underside of the brain is involved in recognizing objects. So it's involved, for example, in recognizing faces. And we'll talk a lot about that in a minute. So V1, V2, V3, you can imagine simple features of being bound together. Oh, there's a box there, but you don't really recognize it as maybe part of a laptop until you reach these lower areas. Now, in V2, V3, you have V1, but the top, if you have another object, and when the the above fires a place over here, and the below fires a place over here. And it's separated from by V1. So these cells are some distance apart. A structure called the lateral occipital complex, LOC here, on the side, you can see that this is where V3 is. This is an important area for determining what that object is, or that it is an object. And what it does is bring together, LOC brings together the upper and lower visual fields. So for example, here you see a lion. It doesn't matter whether the lion occurred above or below, it activates, the lion is on the left visual field, so it activates the right LOC. If the lion was over on the other side, it would activate the opposite side of the cortex, much like V1, V2, V3. But the big difference would be the same cell would fire for the lion here or the lion here, which is different from V1, V2, V3. They would be a line up in here, or another cell would be a line down here. Not the same object in both cases. So V1 had this structure. It had spokes which analyzed form, those lines, those simple complex cells, and it had blobs which analyzed colors. So those are very simple things. As we go through V1, V2, V3, we start putting together that this, for example, might be edges, and you saw how it slowly built up these edges. Okay, as it passed through these structures, V1, V2, V3, and then it put together this rhinoceros. And then that information flows underneath the cortex, the inferior temporal cortex, to recognize different types of objects. A lesion here would produce something called visual agnosia. Basically, you would not be able to determine that there's an object there. If I showed you, let's say, a can of Coke, and you had a lesion in this location, LOC, you could tell me, well, the can is red, it looks shiny, metallic. Well, you wouldn't say the can is red. The thing I see is red. The thing I see is metallic, but I have no idea what it is. And the same thing would happen with the mouse or anything. The same thing would happen to people's faces. They would not be recognized as faces. So there was a famous experiment done by Ungler and Exbury. And basically what they did was they showed a subject, what you'll see here, and they asked the subject to click a mouse when the same face, when the face you're looking at the moment is the same as the one you just saw. So why don't you guys try that? I'm going to click this dot here, and you hit the table when you see the face that you're looking at the moment is the same as the one that was there previously. Good. You notice that every time this face appears, activity occurs in the inferior temporal cortex. Okay. Now, what we're going to do is show you the exact same stimulus, okay, but ask a different question. Is the face in the same location as the one you just saw? So it doesn't have to be the same face. Whether the location was the same. Okay, 1, 2, 3, ready? Good. So notice again, asking this, showing with the very same stimulus, we've now started activating along this street because the question is different. The question is location. Okay, so you're going to make a. So with that simple experiment, you know, these two scientists, Ungulator and Expert, became famous, and they're still churning out papers about these two streams. Now, you should also be able to find patients that have lesions of these different areas, and they should show different symptoms. And you do. If you have a lesion here, you have trouble perhaps grasping a mouse for a computer or a knife when you're chopping. If, on the other hand, you have a lesion on the underside, you have difficulty seeing a mouse among all the different objects. So just looking around the table, you'd see a whole bunch of things, but to determine which is the mouse would be beyond you unless you went around and felt everything, because your ability to sense what an object isn't forgotten. It's just your ability to visually determine what an object is dependent on this structure. Now, one of the areas that was discovered about 10 years ago by Nancy Kanwisher is an area called the fusiform face area, FFA. We'll be talking about this area several times. And this area prefers faces, and it lights up even stronger for a face that you're familiar with. So memory has a big effect on this face. And it's a column would represent, let's say, a particular face. So it would be a cluster of neurons that present several columns that would represent one particular face. Then a bunch of columns beside it that might recognize a different face, slightly different sets of features. Now, if you don't have an FFA, you have something called prosopagnosia. So it's an agnosia. Before we had talked about agnosia, and that was for all objects. And now we have prosopagnosia. So the proso is the fact you can't recognize the face. I wish scientists would just say, face blindness, better than remembering tags and tags of names. Anyways, imagine that if you couldn't recognize a face, you'd be able to tell that there's an eyebrow or a nose. So you'd probably say, okay, that is a face, but who that is would be beyond you. So you'd imagine going into a Loblaws together with a friend, and you separate and meet at the cash register, and you look across the field of people at Loblaws, and you can't pick that friend out because you have absolutely no face recognition. Okay. Hopefully you can remember what color clothes they had or something like that, and from those hues put together that this person is, or this object that you see before you that looks like it might be a person is your friend. Now, amazingly, you could still recognize the identity of someone by other features, the voice, person's voice. So you could be sitting there having coffee, and you know that you're talking to someone who you're talking to. You can recognize them by their gait. It's amazing how definitive gaits are for different people. Each person has a very telling gait. So, areas of this inferior temporal cortex, one of the areas within it is FFA. There's many others that recognize other types of objects. So this one, for example, if I showed it a hippo, a rhino, it doesn't care for it. If I show it a giraffe, nothing happens. But if I show it a lion, a huge amount of activity occurs. So there are groups of cells selective for lions and other groups of cells for other objects. Now, one of the interesting things is that once you get to the FFA, the activity becomes independent of location. So remember that LOC, it didn't matter whether it was above or below the line of sight. Here it doesn't matter whether it's above, below, or to the left or to the right of the line of sight. Now that's a big difference from something like V1 has a big difference from LOC. It means that information from one side of the brain must recross over to the other side. So FFA gets fed by LOC. So LOC on the right and LOC on the left must combine together to define, to produce this thing, a cell that fires no matter where that lion is. Okay? It's selective for lions, and it doesn't care if the lion's to the left, to the right, up or down. It also doesn't care what size the lion is. Okay? That cell will fire the same rate no matter what size it is. Now, if you imagine a V1 cell, only one V1 cell would fire when the lion was in a certain position, and let's say its back crossed the visual field of that small little cell. It also doesn't care what cue you use to define the, the, the lion. Here we're just using an outline to define the lion. Here we're using color. Here we're using texture. There's a slight difference in texture, not color or form, but just texture. And finally, motion will define the lion. So you can see here these individual lines start defining a lion when the lines start moving. Now the interesting thing is that when the lines stop moving, the line fades away. The brain loses its ability to say, okay, this line and this line belong to the same object. Motion has to trigger it. Okay, it says, okay, these two lines are moving the same way. They must belong to the same object. Therefore, I should put them together and see what I see. And you see a lion. Okay. The same in LOC. Well, first of all, it might look the activity might look quite similar in V1. For example, there might be a group of cells here that define the back, and another group of cells here, the same group of cells here that define the back here. So similar cells could be activated by both these objects, but very different cells would be activated in IT because they're different objects. But something like over here, this is a lion, this is a lion. They're defined by, one is defined by form and the other by color. They would light up the very same cell in IT, but very different cells in V1. Now, what's amazing is that if these images appear about 100 milliseconds after each other, and the brain can still sort of take them all in and identify who that person is. It takes you about 100 milliseconds to identify a person that you know. You get a different activity for a larger activity for a person that you know rather than a stranger. Now I mentioned columns. As in every part of the brain you have columns, and in this area, in this IT area, you have columns, and adjacent columns represent similar things. So for example, this 3 columns represent faces from different points of view, and over here would be shapes that are somewhat similar to either the T or the I or an arrow. The other interesting thing about this area is that it's able to put together this view of a face from little snapshots. So your eye points, when you're looking at something up close, your eye points to different features, the nose, I'm not sure what that feature is, the mouth, the eye, okay, but these features, looking at this, it's hard to tell what that object looks like. But when I show you this thing, you can tell it's a nice, cute little girl. Happens to be my daughter, who now has children of her own that look at the same age as her now in this picture. So you can look at your phobia, can look at the eye and the nose and the lips, and immediately put together these different parts and form the face that that, 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 that you recognize. The other thing it does, and this particular thing didn't work. I tried to figure out why not. And pressing this should change the length of the lines. It no longer does. So, and I couldn't fix it. But anyways, what should show is that a line slightly longer on this side would look like a line on this side, where in fact, so you'd overestimate the length of this line because why? Because objects that object is a rectangle. It's a window, and you know that windows have the same length in front and behind. But perspective forces you to imagine, or what you see is this perspective, and you have to, if you become like an artist, through practice, force what you see be changed into what is really there. That this is the length of that line. And for that reason, it takes some time to become an artist, because what the ventral stream is trying to do is trying to figure out what the object is. And so that window, it knows, is a rectangle. And its knowledge of it being a rectangle causes a visual illusion, your sense of perspective. And that sense of perspective, you have to learn to disregard and just paint what is really there, not what you perceive. One of the ironies of life of being an artist. The other thing that happens is that things change depending on how an object is shown. Here, you don't see a Mona Lisa. When she's upside down, you do see your normal Mona Lisa. Seems to go from unfamiliar to unfamiliar. And why is that? Well, again, one theory for why that is that we store our image of Mona Lisa in a sort of a frame of reference. We store her face in a sort of view that is seen most of the time. Okay? So, being a painting, you see the painting most of the time from this particular view, not the upside down view. And so, what you have to do to determine if this looks like what you remember Mona Lisa, compare the lips in the picture to your memory of Mona Lisa sitting here in this coordinate system. And if the picture is right side, it's easy to map the lips to the lips here. But when it's upside down, you have to invert the image of the lips in your mind and then place it against this remembered frame of reference. So it has unusual orientations, and that's what befuddles you. With practice, I'm sure everyone can learn to detect whether that upside down face is the normal Mona Lisa or not. So in summary then, V1 divides into two streams, an action-aware stream that's concerned about the spatial relationships of objects in front of you, and it lets you act on these objects largely unconsciously. So I've been sitting here for the last hour, and I've been moving the mouse around, and I've done that without thinking of where the mouse is and where I have to go to reach it. Okay? So the neat thing about this stream is it's largely unconscious in nature. The ventral what stream, on the other hand, is concerned with the conscious perception of an object, recognizing it and perceiving it. The what stream gets most of the information from the fovea. The action-aware stream gets a large input from ganglion cells that were located in the peripheral retina. Now, in session 5, we'll see that the two sides of the brain aren't equal. The left side specializes in language, mostly in most people. The recognition of words, of sentences. The right side specializes in things like the facial attributes. For example, the facial attributes of a face. So there are two fusiform face areas, but the one on the right is bigger than the one on the left, for a reason that we'll talk about later in the course. In fact, the picture of the face is located here, and the name of the face is located here. May explain why sometimes it's very difficult when seeing a face to remember what the name of the face was. Okay, and we'll see you next week.